Hi everyone, this is Satyajit Das, and in this video, I'm going to talk about EIP 4844 in Ethereum. So this will be useful for people who are interested in Ethereum ecosystem in general and want to gain more insight on the next upgrade, which is called Cancun upgrade in Ethereum. And this will also be useful for people who are interested in becoming a protocol engineer in Ethereum ecosystem. Um, so yeah, I will give a brief overview of what EIP 4844 does and why it is needed in Ethereum. I'm assuming you have some basic knowledge about how Ethereum works and how blockchains work in general. So what is the current state of Ethereum? So Ethereum mainnet that currently processes of the order of 10 transactions per second. So it might be like 30 or 40 transactions, but yeah, it's of the order of 10 transactions per second. And there is no intention to improve on this. That is mainly to ensure that there is decentralization in Ethereum. So if this number we just want to organically increase, if we just want to like change some parameter and increase this to let's say 1,000 or 10,000, then what will happen is that we may need to have the Ethereum nodes may need to have higher computational capabilities and higher storage requirements, which would mean that the decentralization will be low in Ethereum ecosystem. But Ethereum does not want to sacrifice on decentralization, and that's why there is this limit currently, and there is no intention to improve on this at the Ethereum layer 1 level. So but to become a global internet of value, 100,000 transactions per second is needed. That roughly translates into everyone in the world uh, having the ability to make one transaction per day. So how that can be achieved? So in the current scenario, there are something called rollups, which are basically the layer twos on top of Ethereum. So what they do is they optimize for throughput and usability, whereas the layer one like Ethereum, they optimize for security and reliability. So here, as you can see, the Ethereum layer one, which has around 10 transactions per second. Then rollups built on top of Ethereum, and then they do some sort of sacrifice in terms of decentralization or in terms of security and reliability, but they are dependent on Ethereum layer 1 for those things, but they optimize for high throughput and usability. And then they achieve around 100 transactions per second currently. Examples include Optimism or Arbitrum. So one key thing to remember about rollups is the fact that they use the block data, which is essentially the call data in Ethereum, and that is a bit more expensive because it needs to be stored in the blockchain forever. So that sort of limits uh, how expensive the rollup transactions would be. And currently, they achieve around 100 transactions per second. So near future is what EIP 4844 is about. It is also called proto-dank sharding. So what essentially this does is the fact that it introduces a concept of blobs. So blobs are essentially data like byte array data, and those are of size 120 KB. And using the blobs, rollups can achieve around 1,000 transactions per second. So in the later slides, I will explain what blob is and how exactly it works. And this is the near future of Ethereum. So Ethereum's next upgrade will include this functionality, and this is supposed to happen before the mid of 2024. And what is the far future in Ethereum? The far future includes full dank sharding. So in case of full dank sharding, what happens? The blobs, their sizes increase up to 16 MB, and those are sharded, which means not every single node has to have all the blobs. Whereas in case of EIP 4844 or proto dank sharding, all the nodes need to have all the blobs, at least all the current blobs. So what happens in full dank sharding is, yeah, we have sharded blobs, each of which are of size 16 MB, and using that functionality, rollups can achieve 100,000 transactions per second. So even though Ethereum at layer 1 level is still around 10 transactions per second, using rollups, the applications can reach 100,000 transactions per second. They can utilize this functionality. So this is the ultimate aim, which is called full dank sharding or full sharding, and that is at least 1 or 2 years away from now. Okay, so more about EIP 4844 or proto dank sharding. So, in short, what EIP 4844 does is that it bolts blobs onto blocks. So, what does it mean? So, we have currently the blocks in Ethereum which store the transactions and state roots and other things. Blobs are like separate data which are like bolted onto the blocks. And why is it kept separately? That is to ensure that we can delete the blobs later on in future if we need it. So a layer 2 or a rollup, they can utilize the blobs to store some data for a certain period of time until every single node in a rollup they are like happy with this data or the availability of the data, and then we may no longer need it in Ethereum. They may still need to save it in the rollups, but Ethereum does not need to store it. But Ethereum just needs to store some proof which proves the fact that a blob like this existed at some point. So, because the blobs are supposed to be ephemeral, that's why they are kept separately from the block, and each blob has its corresponding block. So, one block can have multiple number of blobs, and how many maximum blobs it can have, yeah, that is a parameter that can be chosen. So this is the TLDR of what EIP 4844 does. So at its core, it is quite simple what it does, but the way it is implemented, that is more complicated than you may expect. And I will, in the later slides, I will talk about why it is the case. And the main reason is essentially to support full dank sharding in future, which is not necessarily needed right now, but our life will be much easier after 1 or 2 years when actually full dank sharding is implemented. Okay, so there is this slide shows some comparison between block space and blob space. So blocks and blobs both are visible by all nodes. So all the nodes have to download all the blocks as well as the blobs. In terms of longevity, the block is supposed to be forever, whereas as I said before, a blob is supposed to exist for a few weeks only, after which it gets deleted. But a reference to that, essentially like a commitment or like a hash to the blob, that is stored, but the exact data can be deleted from Ethereum layer 1. And when it comes to visibility to EVM, block space, it is visible to EVM, but blob is not visible. What this means practically is the fact that the smart contracts, they will not have any access to the actual blob data. And when it comes to actual storage, the blocks are stored in execution client and blobs are stored in consensus client. And in terms of size, yeah, the blobs are targeted around 40% of the block size. So essentially, like three blobs, the target will be three blobs per block, and each blob is 128 KB. So three blobs is 384 KB initially. And when it comes to pricing, the block space is expensive. It is 16 gas per byte, whereas a blob is supposed to be super cheap. And why it is cheap? Because you don't have to store it forever. You only have to store it for a few weeks. So essentially, blobs are have bounded storage cost, no execution cost, but every node bears a bandwidth cost, which means when a blob is created, then it needs to be propagated across the network. So there will be extra bandwidth cost. Okay, so up to the blob, like what exactly a blob looks like in the code. So in the code, yeah, this is an actual line of code from Ethereum code base. So this is essentially a byte array, and which is of the size 131K, and this corresponds to 128 KB size to be exact. So this is how a blob looks like, and inside this, what has to be stored, that depends on who is submitting the blob transaction. So if there is a new type of transaction called blob transaction, and that will carry the blob to the blob pool. So there is something called a blob pool, which is newly constructed. It's different than normal transaction pools, and these blob transactions can be submitted by anyone. It can be submitted by an application, or it can be submitted by a layer two, like a roll up. So one example can be that if an optimistic roll up wants to use this blob functionality, they may combine all their transactions along with some fraud proofing mechanism inside this blob, and then submit a blob transaction which will carry this blob to the Ethereum network. Okay, so the way Ethereum layer 1 is going to support the blob transaction is independent of what exactly is getting stored, as long as a blob looks like this. And when you submit a blob transaction, you submit a blob along with certain other things which are called commitments and proofs, and I will talk about them a bit later. So essentially the point is the blob looks essentially like this, and it is pruned after every 4096 epochs. Okay, so next comes a commitment scheme for a blob. So what is a commitment scheme? Commitment scheme essentially is used to ensure that once it is created and saved, that data cannot be forged in future, and so that it is computationally binding. So this is how it may look like. So a block will store a commitment to a blob. It can be for multiple blobs, and the size of this commitment is supposed to be like limited, it's supposed to be small, but it has to be computationally binding for this blob. So this blob might be a large data, but only that data will correspond to this particular commitment, and no other data can do this. So this idea is called a commitment scheme, and this idea by itself currently already exists in Ethereum. So it can be done through a hash mechanism, or also it can be done through a Merkle root. So you can construct a Merkle tree and create a Merkle root and give Merkle proofs to prove that you actually have the data, and you have the correct Merkle root for a data. So using Merkle root as well, we can store a blob, and there will be no issue. But in our case, we are doing polynomial commitment scheme to storing of a blob, and I will explain later why. Okay, so here is a slide which explains Merkle tree versus polynomial commitment. So what are the differences, or what are the similarities? So when it comes to data, like how the data is represented, in case of a Merkle tree, it's a vector of values. Whereas in case of a polynomial commitment, it is a polynomial, it's a set of polynomial coefficients. The commitment itself, which I showed here, the commitment itself is called Merkle root in Merkle tree, and it is of size 32 bytes, whereas in case of polynomial commitment, it is 48 bytes. Then the proof of value. So if you want to prove that a particular chunk of data is part of this overall database, then you have to submit a proof, and that proof is called Merkle proof in this case, and its size is essentially scales with log n, whereas in case of polynomial commitment, it is fixed size, so it's 48 bytes. But the real difference comes in here. So this is called is it data recovery capable? So is a Merkle tree data recovery capable? The answer is no. You will need every single the vector of values, every single component of that, to construct a Merkle tree and Merkle root or Merkle proofs. Whereas in case of polynomial commitment, the way it is designed is that you can afford to not to have every single piece of data, and still you will have the ability to reconstruct and get the lost data, the so-called lost data. So this is an important feature that is needed for something called data availability sampling. That is that will come in handy in case of full dank sharding. So this data recovery capability, that is not needed for EIP 4844, but for full sharding, which will scale Ethereum to 100k transactions per second, for that it is needed, which is why currently we are doing the hard work of incorporating this polynomial commitment scheme, which will eventually be utilized in case of full dank sharding. And the specific polynomial commitment which we are going to use in EIP 4844 is called KZG polynomial commitment scheme. So I will explain very briefly like what exactly are the steps in case of KZG commitment scheme. So as you know, in case of a Merkle root or Merkle tree commitment scheme, you will essentially create a Merkle tree and then hash together different branches and eventually arrive at a Merkle root. And you have the Merkle root, and you can submit any Merkle proof, to prove any existence of any data. So in case of KZG commitment scheme, the steps are very different. So there are essentially like 4 stages. So setup phase, commitment phase, opening phase, and proving phase. So setup phase is done much before. So in case of Ethereum, it was called KZG ceremony. So what it does, it is essentially it finds a series of points which may look like this. So here G stands for generator. So essentially it can be like a point uh, on it can be a point on an elliptic curve, and we need to find various powers of G. So G to the power alpha, G to the power alpha square, up to G to the power alpha to the power T. So here the important thing to remember is that the alpha should be a secret. So if you know alpha somehow, then the whole commitment scheme will be useless. So you have to ensure you have some alpha which is like completely secret, and you generate these pairs. So to generate it with some alpha that is unknown, there is this concept called KZG ceremony which Ethereum did. And what happens in that is that let's say it's your turn right now. You will guess some alpha on your own, and hopefully you will not share it with anyone. Then you create these values. Then you pass it on to, let's say, me, and I will add some other alpha, and so on. So as long as at least one of us has been honest and created the randomness correctly, then there is no way to actually figure out what is alpha. So after a KZG ceremony, you end up with a list like this. And then comes the next 3 steps are part of the actual blob transaction creation. So when you actually create a blob, you essentially convert the blob data to a set of points, and you create a polynomial which passes through all those points, and that polynomial may look like this. Okay, and then you create this value which is C is equal to G to the power phi of alpha. So you don't know alpha, but you can calculate G to the power phi of alpha because you know all these things. So you utilizing these values and feeding it into this equation, into this polynomial, you can create something called C, which is the commitment. So in this case, this is the commitment that you will create while you are creating a blob transaction. And then you submit the transaction to Ethereum ecosystem. And then the next 2 steps are essentially, you can say, opening phase or the challenging phase, where somebody can challenge you to prove that you actually know this polynomial, which essentially means you also know the corresponding blob data. So for in this opening phase, you need to give to a challenger these 3 things. So you might be asked to open up the polynomial at a random point s. You have to calculate what is phi of s. Because you know the polynomial, you can calculate phi of s. And then you have to calculate this C of psi of s, where psi of s is this function. And this function because phi s and yeah, this function so you can calculate the corresponding commitment. So once you give these 3 to a challenger, then what the challenger has to do is essentially check for this identity. So this identity, the key information to keep in mind is that this identity includes alpha, but you don't need to know the alpha to calculate this identity. Okay, and E is the something called pairing, and that's like out of scope. But the point is, you don't need to know alpha to check this identity. And if this identity holds true, that means that is a proof of the fact that you have the correct data in place. So this is a very brief overview of how KZG commitment scheme works, which is supposed to be used in in case of blob transactions, and the actual usage will happen when we go to full dank sharding. So what happens in that case is that you don't need to have all the chunks of blob data, but you may have some chunks of it, and then you can still be able to prove that you know or you used to know the whole the blob data, or if a network as a whole knows the whole blob data. So every single node does not need to have the entire database, but the network as a whole needs to have it, and you can query the network using these type of steps to know if the network truly holds the correct data. Okay, and these are some links which I put together so that you can have a much better idea about how it is going to be coded. So this one is an L2 submitting a blob transaction. So in this case, it is off-chain labs. They are essentially there is code here showing how a blob transaction is actually getting submitted. So yeah, here as you can see, there is TX data, and you create a new transaction and you send that transaction. Then there are these code links for blob transaction actually getting received in a P2P network, then blob transaction getting into the blob pool, and yeah, they are getting broadcasted, and the consensus layer actually requesting blobs before they create a block. Then they generate sidecars, and then they broadcast. So sidecar is essentially a wrapper around the blobs. So sidecar usually has the blob data as well as their corresponding commitment and proofs. And yeah, the sidecars need to be propagated and received. So these are some links which you can explore to exactly have a hands-on view of how it has been coded so far. So yeah, this is a very brief overview of how IP484 works. I will share a link to this presentation, and yeah, feel free to ask any doubts in the comment section. Thanks.